Very happy to have Nicole Yunger Halpern here with us today. Nicole is a friend of the Institute, and we're delighted that she is visiting us. Nicole did her PhD at Caltech in 2018. She finished her degree there, working on topics in thermodynamics and quantum physics. And then she went on to do a postdoc at Harvard University. And now she's moved over to Maryland and is currently at NIST and also working at the University of Maryland as well. So her expertise is in quantum thermodynamics and related topics. And she has a new book that she has published about the quantum steampunk. So that's going to be really fun. And we'll hear more about that, this evening in her public talk, where we'll have some of her books to also raffle off. So that will be a lot of fun. So we're happy to have you again, Nicole. The topic of today's seminar is why negativity can be useful in metrology.
Thanks for the introduction, and thanks very much for having me back. It's very much a pleasure to be back at Chapman. This book was, or has been recently, a New York Times bestseller. Its description, according to Amazon, is a superstar blogger cuts through the crap to show us how to stop trying to be positive all the time so that we can truly become better, happier people. Now, as Amazon states, this basically means that positivity is not all that it's cracked up to be. And as in self-help, so in probability theory. Probability theory rests on Kolmogorov's axioms. Suppose that we're considering some probability distribution P1 through P. I'll make it discrete for convenience and relevance to what comes next. Then, according to the axioms, all of these probabilities are real. They're non-negative. They sum to 1, and they combine in certain ways. So the probability that our random variable has one of these values is the sum of the corresponding probabilities. Do we always want to use all of these postulates in probability theory? Well, the answer is yes, if we're doing classical statistical mechanics. In classical statistical mechanics, we'll be thinking about some many-particle system, such as a gas in a box. It has many, many, many degrees of freedom, far too many for us to track, so we can't specify its configuration. Instead, we'll list all of the possible microstates that the system can be in, and we'll write down a probability density. This gives the probability that particle 1 is in position x11, while particle 2 is in position x12, and so on, while particle 1 has momentum p11, and so on. We write down this probability density, and we plot it in phase space. We draw one axis to correspond to each of the arguments of our probability density, and the probability density sum law in phase space. In other words, we can represent the state of a classical statistical mechanical system with a probability distribution. This might lead us to wonder, can we represent a quantum state with a probability distribution? By quantum state, I mean density operator. And by represent a quantum state, I mean write down some function of some arguments from which we can calculate probabilities and expectation values. So can we represent a quantum state with just one probability distribution? The answer is not quite, but almost. We have to relax some axioms of probability theory, such as positivity. And if we relax different axioms and make other parameterization choices, then we get different quasi-probability representations of a quantum state. I'll denote the quasi-probability with a p tilde that represents a state rho and has some arguments that we'll see soon. What makes the quasi-probability a quasi-probability? In many cases, if you marginalize over all of the arguments except for one, you get back an ordinary probability. Here, we're marginalizing over all of the arguments except for the jade. And we get the probability that if we prepare a state rho and measure some observable, we get the jade outcome. Quasi-probabilities have been widely used in quantum optics. They've also proved useful, especially recently, in quantum foundations, quantum computation, and quantum thermodynamics. Some of the famous quasi-probability distributions include the Glauber-Sudarshan distribution, the Hosumi-Q function, and the most famous of the distributions, the Wigner function. The Wigner function is famous for being able to go negative. And it's useful for continuous variable systems, but less so for certain discrete systems, especially sets of multiple qubits. The Kirkwood-Dirac distribution is my favorite quasi-probability distribution. It was discovered by Kirkwood in 1933 and Dirac in 1905, and largely forgotten about for decades. People here who belong to Chapman have made great contributions to our understanding of the Kirkwood-Dirac distribution. And in fact, it is Justin who's responsible for my knowing of its existence, because a number of years ago, when I was trying to put together something quantum chaos with something in quantum thermodynamics, I wrote down some really funny looking function and said, Justin, do you know what this is? And he said, it looks like a Kirkwood-Dirac distribution. The Kirkwood-Dirac distribution has undergone a renaissance over the past several years. It's been found to have new applications in many different spheres of quantum physics, from quantum thermodynamics to the foundations of quantum theory. I'm going to talk about an application in quantum metrology, which is outside my usual bailiwick. So I'm going to talk about these papers, which I wrote with a number of wonderful collaborators, especially David Arvidsson-Schucker. I was giving a talk to a group of string theorists, actually, about this quantum chaos application of the Kirkwood-Dirac distribution. David was sitting in the audience, and he said, that looks like something that I need in metrology. I had no experience with metrology whatsoever, but he was kind enough to teach me something about metrology so that we could partner on using this quasi-probability distribution in his context. And I'm going to talk about the work that resulted. Part of it is theoretical and part of it is experimental. But here's where I'd like to go in the rest of this talk. First, for those who are unfamiliar with it, I'll give background about this Kirkwood-Dirac quasi-probability. Then I'll show how we can use an extended version of this quasi-probability to prove that in metrology that involves post-selection, when you throw away some of your data for certain reasons, then non-commutation offers an advantage. En route to that result, I'll show how we can generalize this Kirkwood-Dirac quasi-probability in a useful way. And this result was tested in a photonic experiment by Ephraim Steinberg's group, which is also a set of friends of the Chapman Institute for Quantum Science. And in fact, that experiment sparked some new theory that ended up in that paper. Then I'll talk about opportunities for future work and be very interested in your thoughts. The Kirkwood-Dirac quasi-probability is defined for some quantum system associated with some Hilbert space that has bases A and F. We can think of them as the eigenbases or as eigenbases of observables big A and big F. And if you want to think about degenerate observables, that's fine. Just include some degeneracy parameters in the labels for these texts. This is a representation for some quantum state rho, some density operator. This quasi-probability that represents rho depends on the arguments A and F. And it's a trace with the state all the way at one side and then two outer products next to it. So it's this funny lopsided thing. It's not necessarily a probability. To be a probability, we would need to have these outer products complex conjugated on the other side of rho. This distribution has a few important properties that we're going to make use of. First, it can go negative, like the Wigner function. And there are many known examples of this. If you're interested in a simple example, then one is in an appendix of this paper for pedagogical purposes. Also, this distribution can go nonreal, unlike the Wigner function. So the Kirkwood-Dirac distribution has an extra degree of freedom. Another example comes pedagogically from this paper. Suppose that we have one qubit. Our A and F bases are the eigenbases of the sigma X and sigma Z Pauli operators. And the state we want to represent is an eigenstate of the sigma Y operator. then our Kirkwood Dirac quasi-probability distribution has these elements. Along this horizontal axis, we have the different A states. Along this y-axis, we have the different F states. All of these elements are nonreal. As has been shown by people in this room, the non-real part of the Kirkwood Dirac quasi-probability is related to how we have two observables that don't commute with each other. If we measure one, we disturb the other one. The negative and non-real values of the quasi-probability are sometimes called nonclassical values because they're inaccessible to a probability distribution that represents the state of a classical statistical mechanical system. One useful property of this distribution is that it's experimentally accessible. You can measure it using weak measurements, which don't disturb the quantum system very much. Also, if those two operators that we thought about before, F and A, commute, then they share some eigenbasis. And if you choose for the A and F bases in the distribution to equal that shared basis, then our quasi-probability reduces to a classical probability. Our quasi-probability, which has this definition, will have an F that's set equal to A. So we get just the trace of A with rho, which is the probability that if we prepare a state rho and we measure the observable big A, then the outcome will be little a. Now that we've had an introduction to this quasi-probability distribution, let's see how we can use it in a metrological application. One common task in quantum metrology is parameter estimation. Suppose that we're maybe building a quantum computer and we want for some device to implement a gate. We would build this device as accurately as possible, and it's supposed to maybe rotate a state in some way. But we're imperfect humans, we're not perfect engineers, so this gate won't act exactly as desired. It might rotate the state with a slightly different angle than we intended. So we might want to measure what exactly is that angle that's through which the state is being rotated. And I've set the origin of our number line such that the expected value of theta is 0 and theta is close to 0. Also, I'm going to assume that the gate has this simple form. It's generated by an observable A. We want to estimate theta. How do we do that? We prepare some quantum state rho. We send it into the gates. The gate imprints the parameter on the states, and then we measure the states. We get some outcome, some classical number, little b, which is distributed according to some probability distribution that depends on the parameter. And from the outcomes, we infer about the parameter value theta. How do we quantify the amount of information we gain? We use a metric called the Fischer Information. This is very, very loosely speaking, kind of like the average amount of information about the parameter that we gain through trial. Here's how I think about it. It might not be the best way to think about it, but this is how I personally make sense of it, the definition. Suppose that in some particular trial, our measurement yields the outcome little b. Then we get some amount of information. And the amount of information, the number of bits, is called the surprisal. It's the negative of the log of the probability. Why does that make sense as a quantification of the amount of information? Well, suppose that the outcome is totally determined in advance. We know what's going to happen. Then the probability equals 1, and the log of the probability equals 0. So we get 0 bits of information, which makes sense because we already knew what we were going to get. What we're really interested in is how sensitive this amount of information is to changes in theta. That helps us figure out how well we can recover the value of theta from this probability distribution once we've measured it experimentally. So we're interested in the derivative of this quantity with respect to theta. And we're not interested in only one trial. We're interested in performing a whole bunch of trials. So we should average over all the outcomes we might obtain in different trials. Unfortunately, this average equals 0, but we can square the argument that's being averaged. So this quantity, with this average here and this square, is called the Fischer information. We want to take one step beyond the Fischer information. We said that we obtain this outcome, little b, by measuring the quantum state in some way. We didn't say how we should measure the quantum state. Sometimes we might want to optimize over all possible measurements. As a quick reminder, in quantum information theory, we represent a measurement with a positive operator valued measure, a POVM. It's a set of operators, M sub b, labeled by the outcomes, little b. These operators are positive semi-definite, and they obey a normalization condition. So now, our probabilities associated with the possible outcomes are labeled not only by the parameter value, but also by the measurement we're performing. So this is the same formula that we had before, except the probabilities are also labeled by the measurements. And now we're maximizing over the measurements. That quantity is called the quantum Fischer information. Now that we've established the quantity of interest, I'll introduce a couple of assumptions that I'll argue are justified. First, let's suppose that the input state is pure, because we want as much information as possible about theta. And if the input state is mixed, then our probe system is entangled with some other system. So some of its information has leaked to the environment. And we want all the information we can get, so we shouldn't start with a system that's leaked some of its information. So we'll represent rho with this outer product of size. Once the parameter is imprinted on the state becomes size of theta. We can calculate the quantum Fischer information of a pure state. And the formula is here. The form is not really important to us. I just wanted to show the formula exists. I'll also assume that that generator of the rotation is not totally degenerate. How come? Because we want for the quantum Fischer information to be able to be large. Suppose that we are looking for a way to get the largest possible quantum Fischer information, and we try the simplest thing you can think of. We send into our experiment an eigenstate of the generator A. Then this rotation will imprint the parameter on the state only in the global phase. Because when U acts on the state A, it acts as this exponential, that big A reduces to a little a, and we get a global phase that we can't detect directly, which isn't useful. We instead want for the parameter to be imprinted in a relative phase, and for the relative phase to, in some sense, be sort of as large as possible. What if instead we try inputting a superposition, an even superposition of an eigenstate associated with the greatest eigenvalue and an eigenstate associated with the least eigenvalue? It'll transform under the rotation to the state that has phases. We can pull out this front phase and get a relative phase that contains a gap that's as large as possible. It's sort of as easy to see as possible. The quantum Fischer information is upper bounded by 4 times the variance of the generator squared, which saturates in this case. It equals the gap between those two eigenvalues squared. So this is why we want for the generator A not to be totally degenerate, so we can actually get Fischer information out. Let's alter our protocol a little bit and add a post-selection. Let's throw away some of our data. And we'll talk in a moment about why we might want to do that. We'll send our quantum state into the experiments. It'll undergo the gates. The parameter theta will be imprinted on the states. And then we'll perform an intermediate measurement. This post-selection operator that we'll measure, I'll call F. It's a projector, at least in this theory case. And as a projector, it has 2 eigenvalues, 1 and 0. If we obtain the 0 outcome, then we throw away the trial and start again. If we obtain the 1 outcome, then the state is projected onto some subspace that I'll call F post-selected. And then we perform the final measurements. We get some outcome and we infer about theta. Why would we want to throw away some of our trials? In an example, suppose that the input to our experiment is a photon. It's detected by a photodetector. And a photodetector can saturate. Once it detects a photon, it has to reset, so it can't detect more photons. So we might want to send into our photodetector only the photons that are really worth detecting, that really carry the Fischer information. In this case, the quantity, or a quantity that matters to us, is the post-selected Fischer information. It's, very loosely speaking, the average information that we gain about this parameter from the average final detection. Post-selection has only some probability of succeeding. And if the state passes the post-selection, then it ends up as this state. So it's projected and then renormalized. We can calculate the quantum Fischer information of this post-selected state by substituting into the formula that we saw earlier. And we get a more complicated looking formula that also isn't extremely informative, but we will find a more useful form for this post-selected quantum Fischer information. Post-selection can increase the quantum Fischer information. This has been known. Here's a really, really simple example. Suppose that we send into our experiment a star. It's either a blue star or a red star. And our gates will rotate the blue stars through an angle theta. In our final measurements, we measure how far the star is rotated. If we send in a blue star, then it will get rotated, and so we'll obtain information from our final measurements. If we send in a red star, then nothing happens to it, and we might as well not bother measuring it, because we don't get information about theta. So we might as well post-select. We could perform an intermediate measurement, that is, what is the color of the star? If the star is red, then we might as well throw away the trial and start again immediately. If the star is blue, then we should perform the final measurements and get information about theta. In this case, the post-selected quantum Fischer information exceeds the non-post-selected quantum Fischer information because in the absence of post-selection, our data are polluted by these worthless trials. In this case, you could perform the post-selection, or instead you could perform a pre-selection. You could just throw out the red stars early on. But what if the post-selection and the rotation fail to commute with each other, as is very natural in quantum contexts? That's one of the questions that we addressed in this theory paper. First, we proved that if the generator of the rotation A commutes with the post-selection projector, then the post-selected quantum Fischer information is no better than you could do in the absence of post-selection. We'll just pre-select. To prove this, we use the Kirkwood Dirac quasi-probability. First, we had to generalize this, and this is my favorite step. We had first generalized the Kirkwood Dirac quasi-probability with Justin and with Brian Swingle in this context of chaos in quantum thermodynamics. This is how we define the Kirkwood Dirac quasi-probability. This quasi-probability has two outer products, but why only two? Why not put in as many as you please? Of course, it doesn't make sense just to put in outer products for the sake of putting in outer products. The number should be motivated by physics. And in our case, we needed 4 outer products. In this case of metrology, it makes sense to define an extended Kirkwood Dirac quasi-probability with 3 outer products. This A and this A prime are eigenstates of the observable big A that generates the rotation. And again, if the observable has degeneracies, then you can put a degeneracy parameter in. then we can rewrite the post-selected quantum Fischer information in terms of this extended quasi-probability. This is the formula that we wrote down earlier for the post-selected quantum Fischer information. I said, let's not pay too much attention to it. This is the version that we should pay more attention to. What's really important about it is that it contains 2 copies of this quasi-probability. Now, suppose that the generator A commutes with the post-selection projector A. Then, as we said at the beginning of the talk, this quasi-probability, these observables will share an eigenbasis. And we can choose for that eigenbasis to be the eigenbases in the quasi-probability. And then also, as we said at the beginning of the talk, this quasi-probability reduces to a classical probability. So we can use all of those axioms of probability theory in the rest of our proof to prove that the quantum Fischer information is upper bounded if everything commutes, or if these 2 observables commute. That is, the quantum Fischer information is no greater than it is in the absence of post-selection, which we saw earlier. So post-selection doesn't help us in the absence of noncommutation any more than just pre-selection does, as in the star example. However, in some contexts, it is natural to consider noncommutation, and it turns out to be able to help us. It is possible to observe a post-selected quantum Fischer information that exceeds the greatest quantum Fischer information possible without post-selection. And if you observe this anomalously large post-selected quantum Fischer information, then you can conclude the reason is the quasi-probability contains negative values, which, as we saw before, means there's noncommutation. So that generator of the rotation fails to commute with the post-selection projector. And noncommutation is rather important in quantum theory, which is somewhat satisfying. So noncommutation offers an advantage in metrology that involves post-selection, as shown by this extended Kirkwood-Dirac quasi-probability, which is one of the reasons why I love it. You might be concerned. The probability of a post-selection succeeding could be low. So you could be waiting a long time for any trial that succeeds in the post-selection. However, in an experiment, every operation has some cost. And in some cases, the final measurement might cost the most. For instance, we talked about that photodetector that saturates. So the quantity that really matters is the information we get per unit cost, or the information we get from n trials divided by the cost of n trials. The information from n trials is proportional to the number of trials. It's proportional to the probability that any trial succeeds, and it's proportional to the Fischer information we get from such an average trial. The cost of n trials also is proportional to the number of trials, and the cost of a trial depends on the cost of the preparation procedure, plus the cost of the post-selection, plus the cost of the final measurements, if that final measurement succeeds. We're interested in cases in which the final measurement is much greater than the other costs, so we can approximately neglect those. This fraction approximately reduces, some of the factors cancel out, and the result doesn't depend on the post-selection probability. So the non-commutation can help independently of the post-selection probability. Yes?
When you say that you're interested in cases where the final measurement is more costly, do you mean when it's the least likely to be obtained, or what makes it more costly?
The measurement could cost in terms of time or equipment. Our favorite example is the example of a photodetector that saturates, and so has to take some time to reset. So if you try to send more photons at it while it's resetting, then that's sort of all of that is lost, and it doesn't help you. And so the dead time of the photodetector is what we would call the cost.
Okay, so just completely experimental realities of like,
yeah, or say you don't have. experiments like LHC could produce a ridiculous amount of data. Maybe in your experiment in your lab, you have a finite amount of memory and you can't exceed that memory, so you need to throw away some of the data, reasons like that.
And then the cost of the like post-selection ones, does that have to do also with how likely it is to obtain that measurement, the one that you want? Like you have to factor that in, because every time you don't obtain it, right, you have to restart, so.
But yeah, in some cases, the post-selection could actually not really cost anything at all. And I'll give an example of that in a moment. The N here is multiply all of the post-selection cost so that we're accounting for the post-selection cost in every single trap, whether or not it's ended. So this theoretical result was tested and extended in an experiment in Ephraim Steinberg's lab. We worked with Noah Luku Gladstein and Batuan Yilmaz, who are PhD students who did most of the work. David Arvidsson Shuker and I were providing theoretical help. So did Aaron Brodich, who at the time was a postdoc with Ephraim, and Arthur Peng was another PhD student in the lab who participated in the experiment. The probe sent into the experiment was a photon. It was initialized in the vertically polarized states, which I'll denote by 0. The gate was a rotation with sigma x, so that the state came out in this superposition. The coefficient of the 1 is what really carries the information about theta, because according to assumptions, how we set the number line, how we set the origin of our number line at the beginning of the talk. This cosine theta over 2 is close to cosine of 0, which is 1, and contains no information about theta. Whereas this sine of theta over 2 is proportional to theta. So this is what carries our useful information. In our post-selection, we will ensure that whatever part of the states is 1 will pass through our post-selection. However, the part of the state that's 0 will get reduced by some factor r squared. This is implemented with a partially polarizing filter.
I have a second.
Yeah.
In your theoretical analysis, you assumed that post-selection was always a projector. Is this it?
Yes, that's exactly where I'm getting.
Oh, okay.
This is not a projector. So we had to generalize the quasi-probability yet again to involve cross operators more general than projectors. In this case, the cross operators are labeled by some outcome little f that's plus or minus, and k plus is the operator that's acting here. Minus is the identity operator minus k plus. The corresponding quasi-probability has the same notation as before. I'm going to reuse the notation, even though it's a little more general. Again, we have a trace. We have the state on one side. We have 1, 2 outer products. But what's in the middle here now is a measurement operator. And this also obeys the property that, or has the property that if you marginalize over all the arguments except 1, then you get an ordinary probability. After the partial polarization, the polarization is measured in the final measurement. So we want to infer about theta. Then the experimentalists also measured the quasi-probability. They did that in separate trials without performing any post-selection. They just did quantum state tomography because apparently that was easiest for them. And from the tomography, they reconstructed the states and the quasi-probability. Noah, as he was analyzing the data, realized that he seemed to see a proportionality between the post-selected quantum Fischer information and a measure of the nonclassicality in the Kirkwood Dirac distribution. He said, I think I'm seeing this. Can we prove it? And it turned out that we could prove it. So suppose that our initial state is pure. And it has weight only on those two most useful eigenspaces associated with the maximum and minimum eigenvalues of the generator A. Then the post-selected quantum Fischer information participates in an equality. But here we have 4 times the gap squared, which we've been seeing across this talk. What's really important in these brackets, partially, is that we have 2 copies of our quasi-probability. This plus here, remember, is a value of little f, which is we can think of as one of the outcomes associated with our post-selection measurements. And what's interesting is we have maximum over the quasi-probabilities squared and minimum over these quasi-probabilities squared, so magnitude squared. So this quantity, this difference between the max and the min, we call the nonclassicality gap. We ended up with this proportionality between the post-selected quantum Fischer information and a measure of negativity. We have come up with other measures of negativity, and especially our collaborator, Jose, in another context. This one happened to emerge as useful, naturally. It was very nice to have this experiment that you might think of as sort of just checking does quantum mechanics hold in post-selected metrology, which might not be super interesting. It actually led to the discovery of new theory. So that was really a delight. And also the experiment revealed what are some limitations on the theory. We proved this using the expression for the quantum Fischer information that we already saw in terms of the quasi-probability and properties of projectors and similar tools. Here's one of the most important plots. Along the x-axis, we'll have the fraction of the particles that can pass through post-selection. It's on a log scale. And over here, we have the number 1. So there's no post-selection on the right-hand side. Everything passes through. Along the y-axis, we have the quantum Fischer information per detected photon. We'll also have a log scale on the y-axis. Here's the plot. The different colored lines correspond to the different values of the parameter theta that we want to learn about. The most important line is the one at the top because it corresponds to the smallest angle theta. And so that's where we expect the theory to work best most of the time. There's a little bit of awkwardness on the left-hand side because some of the experimental x's and theoretical straight lines are not quite on top of each other. There was some systematic error. And unfortunately, the post-selection doesn't magnify the systematic error. Although on the other hand, the experimentalists actually use that fact to detect their systematic error and correct it at the beginning of the experiment as well as possible. Again, here's where there's no post-selection. And so this is the amount of quantum Fischer information at no post-selection at the smallest angle. Between here and the most post-selection, there is a 2 order of magnitude difference in the quantum Fischer information. So that's the main results. And also this shows that the nonclassicality gap can be compared to the quantum Fischer information. And in most cases, the stars do basically align on top of the crosses. So the proportionality that we derived can be observed. In this case where, to some extent, we expect the theory to work best with a very small theta and a great deal of post-selection, the conditional quasi-probability, so the quasi-probability that we've been seeing divided by the probability of a successful post-selection, that exceeded 7, which is much greater than the upper bound of 1 we would expect according to ordinary probability theory. Some people might be asking, what is the difference between the technique used in this experiment and weak value amplification, which is another way of amplifying a number so that you can measure it very well. The experimentalists actually chose to name the technique used in this experiment partially post-selected amplification, or PPA. First, in both techniques, we take information that's spread across many trials or many probe particles and condense that information into just a few. However, in the case of partially post-selected amplification, we can magnify any phase, whereas weak value amplification tends to be used to amplify coupling strengths. And in partially post-selected amplification, we use just 1 degree of freedom, just the polarization of the photon. That's used to encode the information about the parameter, and also it's what's post-selected. So you need to keep only 1 degree of freedom coherent across the experiments. Anyone have any questions, by the way? Okay. This might bring up some questions that might be in the backs of your minds. In case you're wondering, we saw that if you see an advantage of post-selection, then it's because of negativity in the Kirkwood-Dirac quasi-probability. Does the opposite hold? So if there's negativity in the Kirkwood-Dirac quasi-probability, do you get a post-selective advantage? And a number of people thought the answer would be yes. Turns out the answer is no. And so an explanation for that is in a theoretical paper that I'll show just in a moment. Similarly, we said that if the quasi-probability distribution has non-classical values, negative values or imaginary values, then it's because of non-commutation. Does the opposite hold? Does non-commutation always imply nonclassicality of the distribution? Again, there were some expectations that the answer would be yes, but the answer again turns out to be no. There's some reasoning in this paper. Also, suppose that you have a Kirkwood-Dirac distribution and you would like to measure how much non-classicality it has. Is there a bound on that? And yes, we can derive bounds. Results are also in this theory paper. This work opens up some more questions. One of my favorite questions is, where might this partially post-selected amplification be useful? We saw that it can be used in a proof of principle experiment that was useful in shedding more insight into this relationship between non-classicality and an advantage, but where could we use it in applications? So a number of times over the past few years, something like the following pattern has shown up. And so it seems like a pattern that could be used in and of itself. Anytime that non-commutation seems to be necessary for some quantum phenomenon, perhaps you can find a physically relevant quantity like quantum Fischer information and decompose it in terms of an extended Kirkwood-Dirac quasi-probability. Then first, suppose all the operators commute with each other. Then the quasi-probability reduces to an ordinary probability, and you can use the axioms of probability theory to bound the quantity, as we bounded the quantum Fischer information. Then suppose that the operators don't commute. Can you prove that the bound can be violated? Then you can show, well, so in some cases, you might be able to prove that this implies contextuality, being very, very careful. So in what cases might we be able to follow this pattern in order to show that non-commutation underlies other useful phenomena? Thinking maybe quantum error correction or magic in quantum computation, since those are very important phenomena that might strictly rely on non-commutation. So have you ever bought something on Amazon and then been told at the bottom of the page, customers who viewed this item also viewed these items? But if you view the Wigner function, you might be interested in the Kirkwood-Dirac quasi-probability. So again, the Wigner function is very widely used, but it definitely has its limitations, whereas the Kirkwood-Dirac quasi-probability is well-defined, even for sets of qubits. So I'd be interested in seeing where, again, for instance, in studies of magic and quantum computation, the Wigner function might usefully be replaced with the Kirkwood-Dirac distribution. In summary, we had a little introduction or review of the Kirkwood-Dirac quasi-probability. We saw that we can use it in order to prove that post-selection offers an advantage in metrology because of noncommutation, or because of negativity in this Kirkwood-Dirac quasi-probability. Actually, an extended Kirkwood-Dirac quasi-probability, we can generalize it for our purposes. This theory was realized and then extended in a photonic experiment, and there's still much to be done. Thanks for your time.
Hey, thank you, Nicole. Questions? Okay.
Yeah, so I've been wondering if there's a connection between this quasi-probability you introduced with the Kirkwood-Dirac quasi-probability with the Wigner function or any other representation. I ask this especially because you introduced this extended definition using POVMs. So I was wondering if you take, for a harmonic oscillator, for example, you take the coherent states, do you get something like P distribution back? Is there a connection between the other representation or other quasi-probability distribution?
Actually, Justin pointed me toward the answer a few years ago. So at least if you take the conventional Kirkwood-Dirac quasi-probability, you can perform some transformations to get some of the other quasi-probabilities by integrating with some kernel. I haven't tried to do that with one of the extended distributions or the version that's generalized to POVMs.
Questions, Matt?
So the connection to contextuality is quite interesting to me. So in the case of quasi-probability distributions that are real, we have this theorem originally due to Speckens and later extended, which establishes a connection between negativity and contextuality. But as far as I know, we don't have that for distributions like Kirkwood-Dirac one, which can have complex values. So have you thought about trying to generalize that connection to show that if you have a non-classical value, then you have some kind of a proof of contextuality?
And I think it might be interesting to have a conversation about this. Let's see. So first, the way that contextuality has been brought into this Kirkwood-Dirac discussion has been, for instance, someone would show that if you see some phenomenon, observe some phenomenon sort of analogous to the post-selected quantum Fischer informations being anomalously large, then you can link it to an experiment that has the same form as a weak value experiment. And if that experiment is performed, then you conclude that you get some anomalous weak value that implies contextuality. But I agree that it would be nice to have something more direct.
Yeah.
I would be really, really interested in the possibility of using just, yes, let's say extending from negativity to imaginary values, or being able to use just the Kirkwood-Dirac distribution by itself, because the standard result is about how all quasi-probabilities need to have some negative values in order for us to be able to conclude that there's contextuality. I personally don't know how to go about establishing the extension that you suggested, but I would be really, really interested in that. And also Justin made some movements as though you'd been thinking about something like this.
I agree, it would be interesting to establish it definitively. I don't know the answer.
Yeah, I want to chime in and say, at least for pure states, the difference between the weak value and the Kirkwood-Dirac is just a positive factor. So when one is imaginary, the other is imaginary. When one is negative, the other is negative. So I'm not sure what's left to do. I mean, maybe when you go to these extended distributions, it's a little bit more complicated, but that's how it works, at least for the simplest case.
Yeah, for the simple case, that's true.
Okay, other questions?
Actually, I'm wondering just how well behaved it is in that situation. I mean, I remember doing a calculation of trying to, trying to create a projector for a region inside the Wigner distribution that was like smaller than you should, right? Smaller than H bar or something. And I ended up with a parity operator or something completely crazy I don't know. So there's a question to me how, I have no intuition about it, how these extended, but what was particularly surprising is I was trying to do something illegal by projecting in space in a smaller area than I should, and then I end up getting the most non-local thing back in my face. So it's a little, let that be a lesson to us, right?
Do you mean how does this quasi-probability look, say, in the experiment?
Oh, let's see.
He's talking about the Wigner distribution, that you can rewrite it in terms of a parity operation. But
Well, it's just I was just playing off of Matt's question, kind of wondering, as a general matter, how do these things, how badly or nicely do they behave? I guess that would always very much surprise me. I still don't quite understand it. Try not to do illegal things, maybe. I don't know.
That seems like generally a good life rule.
Is that a good moral question? Moral.
Well, there are some pathologies of behavior in these things, because if your two bases are very close to one another, then you're going to get a singular limit as they converge, because you'll go from something that's potentially something that's tomographically complete to something that isn't. Right? You take that limit. So there are some there's some kinds of singular behavior in how these things behave.
So it seemed like it was, state dependent, right? It was very dependent on theta, how advantageous or not this was. So does that mean that you have to vaguely know what theta would be or what regime it would be, or?
Yeah, you would perform some sort of rough estimate of theta beforehand. And I'm told by my metrology friends that this is done.
Okay.
This is done. You mentioned, Nicole, this interesting phrase, partially post-selected metrology. What is partial about your post-selection in your scheme?
It's because of that. Well, maybe I should go back to the slide.
actually closely related to an ongoing experiment here. Interesting things. I may be able to relate your theory to another experiment too.
That would be nice.
I'll see what I can do.
Because of this operator here, the operator will allow all of the part of the state that's in 1 to pass through, and just part of the state that's in 0 to pass through. So we're not entirely post-selecting on one, just mostly. And this is implemented by a partially polarizing filter.
So this is on the polarization degree of freedom, right? And then what do you do with what comes through?
We measure the polarization itself in the horizontal vertical basis. So the polarization is serving as the information bearing degree of freedom and also the post-selected degree of freedom.
So you post-select twice on polarization. Something like.
Or we can use only 1 degree of freedom for both the post-selection and the theta information, because this is not a projector, it's a more general type of POPN element.
Right. And if R is close to 1, does anything interesting happen?
Let's see, then the state would be pretty close to this state.
Yeah.
And in this state, the cosine theta dominates, because cosine theta over 2 is close to 1/2. Whereas this sine theta over 2 is close to theta over 2, which is really close to 0. So the state at the point of the green arrow would still not contain very much information about theta.
Yeah, nice. So like in the weak value case, you would try to project on something nearly orthogonal to that state.
Right, which I think is equivalent to that R being really, really tiny.
Yeah.
I think there's a map there.
So one thing I've always wanted to do, if I ever find a moment of spare time, which I never seem to have, is many years ago, I proved this correspondence between the weak value and the Legge-Gargan inequality. And so coming to your last slide about you need something to plug in to apply your method to. So there have been these theorems. So we proved this many years ago that if you have an anomalous weak value, then you can violate this generalized Legge-Gargan inequality. And people have done subsequent work showing that if you violate this Legge-Gargan inequality, it implies negativity. You have to have negativity to violate Legge-Gargan. Other people have proved if you have an anomalous weak value, you have contextuality. And so I would like to publish a grand unified theory or weak value, contextuality, negativity.
Negativity.
It's all contextual.
Positive.
So maybe we can do that. That would be fun. And throw in some Kirkwood Dirac
Yes. Spice it up.
in metrology.
Also, why not gravity? Gravity has to be in there too. So
Favorite gravity.
That's the grand unified part, right? All right, let's thank Nicole again. Very nice.